Okay.
Thank you. Good evening, everyone.
Good evening.
Thank you for joining us for tonight's forum for the public benefit, the Ellicott Astronomical Regulator. Over the past few months, we've been really thrilled to welcome the Ellicott Astronomical Regulator back to Concord as part of our special exhibition, Transformed by Revolution, thanks to a generous loan from Harvard's collection of historical scientific instruments. The regulator first came to Concord in 1775 when students from Harvard College relocated here during the Revolution. Concord minister William Emerson was permitted to place the famous instrument, then known as the college clock, in the town's meeting house for the public benefit, was his quote, where it inspired awe at the rare planetary events it recorded and pride in the growing field of experimental science. In that same spirit of sharing the regulator for the public benefit, we're delighted to offer tonight's program with the theoretical physicist Alan Lightman, horologist Richard Ketchan, and second-generation clock dealer John Delany, along with our longtime Concord Museum curator, David Wood. David will serve as our master of ceremonies tonight, leading a conversation with Richard and John about the history, craftsmanship, and significance of the regulator. And then Alan will come up on stage here and help us understand the instrument as a sophisticated scientific tool used in 1761 and 1769 to observe the transit of Venus and to advance global astronomical knowledge. We'll conclude with some time from questions from the audience, so please start to think of your questions. I hope you enjoy the program, and I'm going to pass the mic back to David.
Good, great. Well, thank you. So I wanted to, a number of you had an opportunity to take a look at the gallery where the regulator is just now upstairs, but that's what we're looking at as a view of that gallery. I just wanted to start there to talk just briefly about the circumstances of this machine coming out to Concord. So behind the objects that you can see there, there's a graphic of an engraving. Well, that's Paul Revere's engraving of Harvard's campus in 1767, blown up large. And to the left of that, behind the regulator in its mahogany case, that's Stoughton Hall behind there, which is a residence hall. But in this same gallery is a newspaper that says right on the masthead, printed at Stoughton Hall. And it's dated 1776, early 1776. And so that's what happened. Harvard's campus was on the front line after April 19th. Boston is surrounded. The siege of Boston is underway. Cambridge, Harvard is on the front line. And the campus was taken over both by the military, by the first provincial troops and then the Continental troops when General Washington arrived, but also by the state, which among other things, took part of Stoughton Hall to use as a print shop. Further to the left, you can't see it in the engraving here, was Harvard Hall, which was built in built about 1650. And that housed Harvard's scientific instruments, what they called the philosophy chamber. And it also housed their library, some 5,000 volumes. Well, it burned in 1765. There was smallpox in Boston, so the Provincial Congress moved to Cambridge out into the country and left a fire going and burned the place down. And it was a terrible loss for the university. Not only their 5,000 books, but their scientific instruments were gone. So they immediately set about replacing them. And with the assistance of Benjamin Franklin, who was agent for the colony in London at that time, acquired the piece that we're principally talking about tonight, the Ellicott clock made by John Ellicott in London in 1765. So Allison mentioned that it was in the meeting house because at the special request of William Emerson, the minister. William Emerson was ended up being the grandfather of Ralph Waldo Emerson. So William Emerson petitioned the faculty for permission to put this timekeeper on view for the public benefit. And the reason it was for the public benefit is because the public knew what this thing was, knew what it was doing. And it was participating in an event that was international in an astonishing way. I'm reminded of what's going on now in Provence with the tokamak. Virtually every nation is involved in that in one way or another. And that's what was going on in the 1760s. And you could read about it in the Boston newspapers. John Winthrop, who is in the portrait in the center, portrait painted by John Singleton Copley. And you can also see the telescope in the portrait is the telescope that's on in the case there. Winthrop is the professor of natural philosophy, which is physics, and taught the students by experiment. They were conducting experiments as part of their curriculum. Now, so all that's gone, so they had to replace their equipment. And the particular event that people knew about, John Winthrop wrote a long article about the event Allison mentioned, the transit of Venus. So the public in Boston has been reading about this since 1761, and now it comes to be 1769 when this thing comes to the fore. So it was a famous instrument, one of the most accurate timekeepers in the world at the time, and that's what we want to talk a bit about first. I'm just showing you the dial of the Ellicott, and I'll just mention you can see 3 dials there. One at the very top that's a way to regulate the pendulum. The one below it is seconds. The long arm that you can see, that's minutes. And then in the aperture, in that little window there, that's the hours indicator. So we'll maybe talk a bit about why they're separate. But and at this point, unless Richard, you have anything you wanted to say about the dial, we could move on to the escapement.
Well, I like to think of the dial as emphasizing what was most important to the astronomer, and that was the seconds and the minutes. They really didn't care about the hours, so they're kind of hard to see.
I mentioned this is a fiercely accurate machine. We're going to hear why accuracy matters later on, but we wanted to hear from Richard a bit about the features of this that improve its accuracy. And we'll begin here.
Well, there's several things that a fine regulator that keeps very good time needs. It needs to have a good escapement, and this shows 2 versions of an escapement. The one on top is very, very close to what's in that Ellicott clock, and that's what's called a deadbeat escapement. The one on the bottom is an anchor escapement, and every time it ticks, it backs up the whole gear train, which doesn't do the clock any good. And the reason that they want to have that very fine escapement is that the pendulum is not what they call isochronous. It doesn't keep the same time if it was beating with a wide arc or a narrow arc. So they want to keep it beating the same, and they would like it to be fairly small. And that escapement was capable of doing that. And you can go to the next one. And this is a picture of the pendulum. And one of the problems that they had with these clocks was that as the temperature changed, it changed the rate of the clock. It kept a different time. If it was cold, then the pendulum shrunk a little bit, it got a little smaller, and it went faster. And if it was a very hot day, the pendulum would be longer, and it would go a little slower. So they had to find a way to compensate for that. And this is usually done bimetallically. If you have two different metals, they will have a different coefficient of linear expansion, and you can take advantage of that to, in this case, actually make the pendulum bob go up and down just a very tiny amount to keep the center of mass exactly the same. And this does it with a brass rod and a steel rod, and they're attached solid together at the top, so down at the bottom they kind of move like this, but certainly not as much as I'm moving my hands. And that really wasn't enough to compensate, so Ellicott decided that he was going to emphasize that movement by putting some levers in there. And that seemed to work quite well, except that the pendulum was very, very heavy. That pendulum was probably 20 or 25 pounds, and that was a little bit too much for those levers. So on the bottom, they put a spring that takes most of the weight of that pendulum, so that those little levers are actually moving that up and down very easily. And that's, in the business, we call that a bow tie spring. And I'm kind of partial to bow ties, so I like that. The other thing that was interesting about this pendulum was that oftentimes you needed to adjust the rate of compensation for temperature. And if you had a mercury pendulum, you could alter the amount of mercury that was in the jar. And if you had a pendulum like this, you had two screws on the outside there that would change the length of the lever so that it would either compensate more or compensate less, and you had to fool around with those and get it just right. The nice part about those screws was that they are moving horizontally and not up and down, so it means you didn't have to regulate the pendulum all over again to keep time in order to use it. So if you had the mercury pendulum, you added mercury, then you had to retime the pendulum before you could even get down to fooling around with the temperature compensation. So that was an improvement. And this is a pendulum that Ellicott designed and built.
Great.
So,
And it had so it stayed in production for a little while, and what we're going to hear from John is another example of the same sort of pendulum. So John, if you can tell us what we're looking at here.
So this particular example was signed by Joseph Pope, who was a Boston clockmaker, watchmaker. He started building clocks in the early 1770s and repairing watches along with his brother. And Joseph, more than his brother, was a very well-educated man. He gave a number of papers to the scientific community at Harvard about all kinds of things related to clockmaking and scientific endeavors. Joseph Pope was famous, probably most famous for building an orrery at Harvard, which is still there. And it took him 12 years to build this apparatus. The story is told that he built it at night when he wasn't working during his daily life. And on a whim, a person by the name of Waterhouse, who was famous began Harvard's medical school, got to go see it and was just overwhelmed by it, and told Governor Bowdoin about it, who was another Harvard, another big figure in Harvard's history. And they decided that Harvard should really have a look at this, that this was so special, this orrery, that it shouldn't leave the state. And they put a committee together. The committee said it was fantastic, but they neglected to buy it. And although Pope wanted 450 pounds for it, it's a very big piece of machinery. It's 6 feet across. Bowdoin decided that they were going to petition the state legislature. They actually had a lottery for it, and they did raise the money, mostly through Harvard's subscriptions, and they put it in Harvard's collection. Pope had a lot of money in his pocket at this point, and prior to actually having it sold to them, he was really discouraged with not being able to sell it here in America. He said that the population was too poor to buy such a wonderful machine. And he planned to go to Europe, to England, to sell it. And he actually delayed his trip after it was sold, but did go there with a letter from Governor Bowdoin Waterhouse saying that he was such a competent and learned man that he should be easy to be employed there. And you'll notice that this is dated 1780. Well, Ellicott died in 1772. It's my contention that when Pope went to England and started talking to their scientific community about scientific things, that he had the opportunity to buy this pendulum and brought it back and put it on his own personal clock. He was so enamored with the technology that he thought it fitting to put on his own personal clock, which we'll see in another slide or two how wonderful that was. And this is the dial of Joseph Pope's personal clock. It was used for a time as the Boston Standard Timekeeper. It was also used for a time up in Hollowell, Maine as the Maine Standard Timekeeper. He moved to Hollowell.
What time is it?
It depends on where, it depends on which time zone you want to be, which you'd like to be notified of. But you'll notice it's the 24-hour dial, and there are 23 brass hands. The 2 hands that are off color, the steel hands, tell you local time, Boston time. So on all of those other hands, if you look at the engraved disc, it actually shows you places on the globe. And of course, it would indicate the time in that specific spot.
And there's another feature on there too that I wanted to.
Yeah, so again, we go back to the orrery. This is a planetarium, and it is tracking the location of 6 planets, as well as where they are in the calendar. And this is all incorporated in the design of the mechanism. At the time in Boston, of course, Bostonians thought that this is one of a kind. It turns out that David Rittenhouse in Philadelphia had made a couple of similar things, and still a very special thing. Probably the most complicated, and in my opinion, the most important clock made in Massachusetts.
Nice. Well, we're going to have a little technical change, or a little technical shift here if we can. So I'm going to turn over my microphone to Alan Lightman. No, I'm going to turn it over to Allison, who knows what to do with it, actually.
Your shirt.
Just put this in my pocket. Okay.
Want to sit here?
And then you can click on the
Yes.
computer.
Okay. Welcome. It's wonderful to see so many people here in this world-class museum. So what you see here is what human beings have been looking at for about 300,000 years. That is the night sky. And of course, we're still as mesmerized by it now as they were 300,000 years ago. But the night sky raises a lot of questions. First of all, what are those points of light? How far away are they? Do they go on forever and ever? Because when you look at the sky, you see only a two-dimensional painting. You don't know how far those points of light are. One of them could be very bright and far away or dim and close by. You just don't know. So we really didn't know much about the sky, our place in it, until we could measure the distances to those stars. The first person to measure an astronomical distance, a large distance, was Aristophanes, the Greek, in about 250 BC. And what he realized is that if the Earth is round, when the sun is directly overhead at one point on the Earth, if you look at it from a point north of that, it's going to make an angle at the highest point. He had a very deep well at Syene, and when the sunlight hit the bottom of that well, he knew that it was directly overhead. And this other location, Alexandria, which was 250 miles away, and he knew that it was, the way that he measured 250 miles is he knew how fast a camel walked and measured the length of time it took the camel to walk from Syene to Alexandria, about 250 miles. And the sun at high noon at Alexandria made an angle of about 7 degrees with the vertical. And looking at this picture, he drew this picture, he figured out the geometry, that 7 degrees is about 1/50th of a circle, which is 360 degrees, and therefore the distance between Alexandria and Syene was about 1/50th of the total circumference of the Earth, giving a total circumference of the Earth of about 25,000 miles, which was very close to the right number. So these guys, these ancient Greeks, were just as smart as we are. They just didn't have computers and cell phones, but they were awfully smart. So now I want to turn to another smart guy, Isaac Newton. And Newton did many things, and one of his least known accomplishments was that he calculated the distance to the nearest star. And he asked the question, how far would the sun have to be as dim as the nearest star? Well, he didn't have photoelectric cells, so he couldn't measure the brightness of a star compared to the brightness of the sun, but he knew that at certain times of the year, the planet Saturn had a brightness about equal to the brightness of a distant star. And he knew what fraction of the sunlight Saturn received, depending on the distance of Saturn from the sun, which is not too different from the distance of the Earth to the sun. And in terms of that distance, he was able to calculate that the nearest star is probably a few 100,000 times the distance from the Earth to the sun. But it was in terms of the distance from the Earth to the sun that he didn't know. So if we knew the distance from the Earth to the sun, we would also be able to calculate the distance to the nearest stars. So next, I want to discuss a very useful principle in astronomy called the parallax method. And that's a fancy word for just saying that if you look at a distant thing from two different positions, the angle shifts a little bit. So the guy on the right is looking at this tree in front of the mountain, and he sees it at that position a little bit to the left of the mountain. The guy on the right sees the tree a little bit to the right of the mountain, and the angular shift just depends on how far away the mountain is and the distance between the two guys. If they're standing right next to each other, there's no shift in angle, but if they're far apart, each one sees it from a different point of view, and the angle of that tree relative to the mountains shift a little bit. That's called the parallax method, and it's extremely important in astronomy, as we'll see. And the clock, well, the clock isn't here anymore, but the clock is going to figure into this. So I shouldn't call it the clock. I should call it the regulator. David mentioned the transit of Venus, and that what that refers to is that the planet Venus and all the planets cross in front of the sun, or the nearby planets do. They cross in front of the sun, and you see it crossing in front of the sun with a telescope because the light of the sun dims just a little bit. And then when the planet gets to the other side, the light comes back to its normal value, the light of the sun. Now, if you're looking at Venus crossing the sun, or the transit of Venus, from two different locations on Earth, the angle, just using the parallax idea, the angle at which you're viewing the planet Venus projected on the sun shifts a little bit because you're looking at it from a slightly different position, just like the position of the tree shifted relative to the mountain. And that means from two different positions on the Earth, far apart, you'll see the sun, the planet Venus, cross the sun at different positions. The top line is as seen from Canberra, which is in Australia, and the bottom line, A prime, is what you see from Svalbard. It's in Norway. I'm mispronouncing that. And these two positions are about 10,000 miles apart. So they're looking at the crossing of Venus from slightly different angles, and so it will take a slightly different amount of time for Venus to cross the sun. Now, if you measure, you know that Venus travels at an angular speed of about 1/10 of a degree per hour. That's the rate it moves across the sky. And we talk about degrees when we're talking about the sky, because when you look up at the sky, you see angular degrees. You don't see actual widths. It's 360 degrees, or I should say 90 degrees from the vertical to the horizon. The sun has an angle of about 1/2 a degree. When you look up, the moon is about 1/2 a degree also. Venus moves across the sun at about 1/10 of a degree per hour. So you're looking at the transit of Venus from two different locations on Earth, or it might be several different locations. You have a good clock or a good regulator at each location. You measure the length of time it takes the planet to cross the sun. And from the difference in those measurements, because you see it crosses a different distance, the top B prime is a shorter distance than A prime. That distance translates to an angle, a parallax angle. And since you know the distance between Canberra and Svalbard, you can compute the distance to the sun. And the distance in transit time was measured in the mid-18th century to be around 2 or 3 minutes. That translates to an angle of parallax of about 1/100th of a degree. And knowing that the two positions are 10,000 miles apart, that gives you a distance to the sun of about 100 million miles. So that was the first, beyond Eratosthenes' measurement of the diameter of the Earth, that was the first astronomical measurement. And of course, going back to Newton, we can then estimate the distance to the nearest star. Well, next I want to talk about a very important woman, Henrietta Leavitt, who worked at the Harvard College Observatory on Garden Street in Cambridge. Harvard and Cambridge are going to figure a lot into this full story. And Henrietta Leavitt, who was not given hardly any credit during her lifetime, she discovered that a certain group of stars called Cepheid variables, that their brightness oscillates. Well, it was known that the brightness oscillates going from dim to dim to bright, like a blinking Christmas tree light. But what she observed with a bunch of Cepheid variables, all in the same location, is that the time for each one to make a cycle was correlated with this brightness. The brighter stars had longer periods between bright, dark than the less bright ones. And once you could calibrate that, you could then measure distances to these Cepheid variables. And this is her calibration graph, where on the left going up is the luminosity versus the pulsation period. And you can see that stars that had greater pulsation periods had greater luminosities. Well, you had to calibrate this diagram with one of the Cepheid variables to calibrate all the rest. And to do that, you measured the parallax of a Cepheid variable that was pretty close to Earth. So again, we're using the parallax method, and we're again depending on the distance from the Earth to the Sun. Well, that was 1912 that Miss Leavitt made this discovery. It's one of the most important discoveries in astronomy, and you'll see why in the next 2 or 3 minutes. This enabled astronomers to measure distances to Cepheid variables, and if you saw a bunch of Cepheid variables in a certain region of the sky, you could measure the distance to that region. In 1918, Harlow Shapley, who was the director of the Harvard College Observatory on 60 Garden Street in Cambridge, he used Henrietta Leavitt's method of measuring distance using Cepheid variables to measure the size of the Milky Way, our galaxy. And I forgot to mention that if you know the luminosity of a star and you compare that, luminosity is intrinsic wattage. That's how intrinsically luminous it is. If you compare that to how bright it appears, that's how you measure the distance to it. For example, if you have a 100-watt bulb and you put it very close to you, it has a certain brightness. If you put it further away, it's dimmer. And if you know the wattage of that bulb, then comparing the wattage of that bulb to how bright it appears, you can measure how far away it is. And that's what Henrietta Leavitt did with the Cepheid variables. That by comparing the luminosity, which is the intrinsic wattage, to how bright one of these appears, you can compute its distance. So that's how she used the Cepheid variable stars to measure distances to these things. And in 1918, Shapley used it to measure the size of the Milky Way, our galaxy, which is about 100,000 light years across. A light year is the distance that light travels in a year. A light beam can go around the Earth about 7 times in 1 second. That's how fast light travels. So imagine how far it can go in a year. And the galaxy is 100,000 light years across. It took a light beam 100,000 years to go from one end of the galaxy to the other. It takes a light beam 8 minutes to go from the sun to the Earth. 100,000 years to go from one side of the galaxy to the other. Well, a few years later, in 1924, the American astronomer Edwin Hubble, he's one of the few people who did not live in the Boston-Cambridge area in our story. He's a California guy. He used this Leavitt's relationship between the luminosity and the period of Cepheid variables to measure the distance to the Andromeda galaxy, which is the nearest galaxy to us. And before that, we didn't know that individual galaxies exist. We thought just stars filled up space. But what Hubble did is by measuring the distance to the Andromeda galaxy, about 2 million light years, which is much larger than the size of our galaxy, he was able to conclude that these globs of stars are actually whole galaxies that are separate from our galaxy. And in 1929, back to Hubble. 1929, he made probably the most important discovery in astronomy, and maybe the most important discovery in all of science, which is the universe is expanding. And the way that he made that discovery, again using Henrietta Leavitt's Cepheid variables, which ultimately depended on knowing the distance from the Earth to the Sun, he measured the distance to distant galaxies. They're all moving away from us. And he found that the velocity of motion of a distant galaxy was proportional to its distance. That is, a galaxy moving twice as fast away from us was twice as far. And if you put dots on the surface of a balloon and start blowing up the balloon, you will find that each dot moves away from a central dot, or any dot you pick. You can pick any dot you want on the surface of the balloon. Any dot moves away from it with a speed proportional to its distance. That is, it will move twice as far in the same amount of time. And that led Hubble and everybody else conclude that our entire universe is like the surface of an expanding balloon. It's getting bigger and bigger and bigger with the galaxies all moving away from each other. And if all the galaxies are moving away from each other, you can play that movie backwards. And at one time in the past, all the galaxies were crunched together in what's called the Big Bang, which we now believe was about 14 billion years ago. So we know that our universe had a beginning, and we know about how long ago that was, about 14 billion years ago. So this is why I say that this is possibly the greatest discovery in science, learning that our universe had a beginning, and it was about 14 billion years ago. And all of this can be traced back to Henrietta Leavitt, which can be traced back to the distance to the sun. So this is really heady stuff. And I will stop there. I hope I didn't use up more than my 20 minutes. Should we have questions now? Should I come up there? What should I do?
I may start with a question if I can get the...
Oh, you want?
This one?
Yeah.
And you're going to field questions in a moment, I'm sure, so I'll pass it back when that happens. But just to follow up briefly on what Alan was saying, the critical matter of accuracy for the timekeeper that's measuring this event. You've now heard why it matters, and certainly the people in Concord in 1769 had an inkling of that. There's much yet to come in the story, but they genuinely had an inkling of it because it's being written up in the newspapers. But as we were talking in the gallery before, the question came up is, well, how accurate is that timekeeper? And John, you suggested about 5 seconds a month.
It's not unreasonable.
And so we just heard from Alan that the critical measurement takes about 10 or 12 minutes, you know, the difference they're looking at. So that means the clock is massively overqualified for recording that duration accurately, and that's why they came so close to the real or to the presently measured distance to the sun. And then before we ask for other questions from the audience, I had a trivial question for Richard, that because I wound that regulator this morning, and it reminded me, most clocks you wind clockwise. This one you wind counterclockwise. So why is that?
Well, this is, most clocks that you are dealing with here in the museum go for a week at a time. And it's got something to do with the gearing. And this clock goes for a month on one winding. And the way that they can do that is they put an extra gear in between the arbor that moves the hands and the one that's got the cord wrapped around it with the weight on it. So it means that you have to go in the opposite direction.
Thank you. Are we looking for... And we'll have to carry them the mic?
No, if you don't mind just repeating it or,
Good, good. Okay, so we do that again. Bill, we can start with you.
Yeah. Who decided how long to make a minute?
I'm not sure exactly how, but it may have had something to do with the sundial.
All right. I saw some, yes.
Will might know.
It's minuta prima is the first small division. The circle is 360 degrees, 24 hours, 15 degrees every hour, and it moves 1 degree every 4 minutes. So they named the first small degree minuta prima, the second small degree, which we call seconds now. All of this came from astronomy. That's called minuta simpli. Thank you.
Thanks. Yes.
Yeah, just interested in comparing the Ellicott clock performance against the Harrison work that was going on at about the same time.
Oh,
That's, is it
Harrison.
Harrison, and he produced 4 models. Any idea of where the Ellington clock fit in that collection?
Richard will, so the question is how, it's kind of rating the Ellicott against Harrison's,
C clocks.
yeah. And I will say, I should have kicked this off, that Richard is absolutely the only person I know, Will, you may know others, who can take Harrison's timekeeper apart and then put it back together again.
I've done it maybe 3 times.
The original is the size of a small closet, and it quickly miniaturized. But so the question is rating, Ellicott versus Harrison.
Well, Harrison was really working on this for a long time, and I'm not sure what funded him while he was doing it, but he spent a lot of time doing this, and perfecting the things that make a clock accurate or inaccurate. Basically, temperature compensation, which is what Ellicott was doing also. But I'm not really sure if Ellicott's regulator was any better than Harrison's. I think Harrison's might actually be better. And one of the...
There was no competition. Harrison did not like it because he considered it plagiarism. Ellicott had taken his idea and of brass and steel rods, and he had created this much more complicated device where you used 2 levers. And what would happen is it would jerk suddenly when it was expanding. It wouldn't necessarily go very smoothly. I think the spring at the bottom
Which is, that helped, yes.
that helped it. But there was no love lost, I think, between them. And Harrison, devoted so much time to marine timekeepers. But the clock that he was making at the end of his life was a friend of repeated, using Harris's technology, modern materials, after 2 years of working, it lost half a second.
Wow.
Most of it never wandered off, and this was in a formal test at the Royal Observatory.
It was at Greenwich that they were testing it, wasn't it? Yes.
I want to just add a comment. We've been talking about the way that temperature changes had to be compensated for in these clocks. And the reason that is because the period of a clock, which is of a pendulum, which is the length of time it takes to make one swing, depends upon the length of the pendulum. And when the pendulum expands, that effectively, or contracts, that effectively changes the length of the pendulum, which then changes the period, the time to make a complete swing. So that's why you had to somehow compensate for the change in length due to change in temperature.
Thank you.
One thing there's also barometric pressure, which Harrison understood, but he didn't have a name for it, so he called it the weight of the air. So in 1727, when he was timing his clocks, and his wooden regulators would keep time for a second a month, and people in London said, well, how do you know it's a second a month? And he said, well, I stand in front of my window frame and I look at my neighbor's chimney. My brother actually calls out the time when the star disappears at night. And then the next night we watch it, and he's rating his clock to sidereal time, which is 3 minutes 56.4 seconds faster than solar time. And he would time it, and when the great clockmakers in London like George Graham heard of this, he thought, wow. Okay, and to answer your question, Graham lent him £100 free of charge, and a number of other people came to his support so he could build his marine timekeepers.
Brilliant.
You're talking about this regulator being here in Massachusetts, which is so, and you're talking about the transit of Venus being measured in Canberra and Svalbard. What do they use for their regulators? Like, we've got one of the best regulators in the world sitting here.
Well, one of the observers was James Cook in Tahiti, and Cook had Harrison.
No,
He had,
Shelton clock,
Shelton.
clock by John Shelton.
Yeah.
Shelton made most of the regulators. He'd worked with George Graham, who was a great clockmaker in London in the first half of the 18th century.
Great. And that's another of those indicators of what a big deal this observation of the transit of Venus was. England sent James Cook, built the Endeavour, sent James Cook to Tahiti. And was it on that occasion that he came across the Sandwich Islands, or another time? But that's how big a deal the thing was. So there were accurate timekeepers at the various stations, but I'll take all the way at the back.
I'm sure I can use a big voice.
Okay.
Italian household, so I can speak loudly. I was just curious about the transit of Venus. So to the observer, the planet seems to go like from left to right across the sun. But is the sun's moving too, at least to the observer, the sun is moving toward the one turning. Do you have to account for the fact that it takes a little longer if the sun's also running away?
Yes, you do. I think that in practice, what the observers actually measured is not the full time for the planet to go across the sun, but for the duration of time when the light first started dimming to when it dimmed all the way. So when the planet first made contact with the sun to the time when it was fully inside the sun. And that time is only about 10 minutes. So the sun didn't really move that much to mess up the observation in that period of time.
Thank you.
So these clocks are extremely accurate, but at the time, what did they use to calibrate them?
They were using an observatory.
Okay, so the sidereal time.
They had a transit telescope, and they were using sidereal time, as Will said. and they could translate that into our regular mean time.
There's one.
Besides navigation, why was the transit of Venus important?
Why was the, apart from navigation? I wouldn't say it's necessarily directly related to navigation, but the importance of that careful observation is what Alan was speaking about, is that the datum, the ultimate answer they got from that is the distance from here to the sun, which filled in these partially answered questions like the one that Newton asked. So that was why this particular event, that was the benefit there. And there's a.
Are there any significant mechanical differences between the Ellicott and the shipboard regulators that were used?
Absolutely. The Ellicott regulator has a pendulum, and you can't use a pendulum on a boat. And they had a balance wheel, or Harrison's version of the balance wheel, which were a couple of oscillators that were going back and forth. And eventually, they wound up using just a little tiny balance wheel like you have in a watch. But you can't. I think Christian Huygens went to his grave trying to make a pendulum work on a boat, and it just didn't work.
You mentioned that temperature is the primary source of error, one of the primary sources of error that the regulator was designed to address. But in the case of a balance wheel or something much, much smaller, where the degree of shift as a result of expansion, differential expansion, is more limited, is it really still temperature that needs to be compensated for, or is it motion and other influences?
It's temperature, and if you look at a pocket watch, you will usually find that it's got a bimetallic balance wheel, and it actually expands and contracts. Nowadays, they've taken the artistry out of the hands of the craftsman, and it's gone into the hands of the metallurgist, and they have materials that don't expand and contract, or do so small that it's insignificant.
I imagine the mechanism is pretty delicate as far as moving the clock. You must have to do a lot of work to secure the mechanism before you can move it?
Yes, we took it all apart. Well, not completely apart, but we take the movement and the dial out and pack that up separately. And when I do that, I get to use one of my favorite clock tools, which is a pipe cleaner. So you can take that pipe cleaner and you can tie off a couple of the things that would normally oscillate when you are moving the clock around. You just tie them off so they don't move.
So are we talking multiple hours on both ends?
How long did that take us? Multiple hours on both ends. I went to Harvard and took the clock apart for shipping, and we had people there who are art movers. I'm no longer allowed to move a clock at Harvard anymore. They have art movers who move the clock. But I take it apart and I put it in the box and make sure that everything is secured. And then when it gets here, I really had to restrain myself because I wanted to do everything myself, but you have art handlers here at the museum, and that was their job. So they were taking it out of the case, and then I would pick it up and put it in the clock. And one of the things that they did that I really liked was they took pictures of everything as we went along so that we can put it back in the box the same way that we got it.
What's involved in maintaining the regulator? How often do you service it? How do you do that?
Well, one of the biggest problems with it is the deterioration of the oil. And Harrison got around that by using bearings made out of lignum vitae, which are naturally lubricating. And people back then were using some terrible, in our for us today, some terrible things. They were using olive oil that they had refined. They were using whale oil. And these things all deteriorated, and they got sticky and gummy, and you really had to clean that clock probably every 3 or 4 years if it had that kind of contamination going on in it. Today, I'm using an automotive lubricant called Mobil 1. And it is supposedly totally inert. It doesn't react to the metals. It doesn't get acidic. It doesn't evaporate. It doesn't change, doesn't even change color with the sunlight. And I'm recommending that people have the clock re-oiled maybe every 7 years. But you could probably go longer than that. And that was one of the things that Harrison was trying to get around with his clock, was the deterioration of the oil, which would then cause the clock to change its rate as the oil aged. And there was a story about somebody asked the great watchmaker Breguet why he didn't make the perfect watch. And he said, "Give me the perfect oil, and I will make for you the perfect watch." So.
We have room for one more question, if there is one.
Can I make one more comment? I wanted to make one more comment and then a philosophical comment. The detail that I forgot to mention when I said that Henrietta Leavitt's luminosity period relationship for these variable stars depended on the distance of the sun. What I forgot to mention is that when you look at a distant star, you can't use the parallax method from different positions on Earth because the angular shift is too small. So the baseline for measuring that angular shift is actually the position of the sun, of the Earth on 2 different sides of the sun. And so we have to know the distance of the sun from the Earth in order to know the length of that baseline. Then we look at how much the angle shifts to the star. Then we know the distance to the star for the nearby stars. And once we know the distance to one of these nearby Cepheid variables, then we know its intrinsic luminosity, and then we can use Henrietta Leavitt's chart to measure the luminosity of any other Cepheid star, compare that to its brightness, and then you know its distance. So I wanted to end with a philosophical comment. It's mind-blowing to me that we human beings on our one little planet, which is in one small solar system, which is on the edge of a galaxy, which is one of billions of galaxies that we can see, that we have been able to measure the age of the universe, 14 billion years, and to conclude that the universe had a beginning. And we're doing all of that from our tiny speck on our tiny planet with our short lifetimes, and all of it evolves back to measuring the distance to the sun.
Before you get up, okay, you see it. All right, I was worried about you.